In this lecture, I'm going to talk about 2D array processing, part 2. A 2D array can be declared like this. This is a 5x5 matrix or 2D array. There are 5 rows and 5 columns. This 5-row, 5-column matrix, M, can also be viewed as a 2D discrete function. And 2D discrete function, you have the x and y axis, and the value of the matrix is like Lego, like this. In this lecture, I'm trying to explain how the index of 2D array works. Indexing is the solution space, so it is very important. First, let's look at the nested loop. 2D array is often being processed by nested loop because we need 2 indexes to handle the row index and the column index. So the outer loop, we have the I index. Inner loop, we have J index. Each time we update one outer loop index I, and then we finish one iteration for all of the columns for the inner loop. And before the loop, we will have the outer loop processing before part. Then we enter into the row loop. And then in the row loop, we will repeat several times of the inner loop. And before that, we can put some processing over here. And then in the center of the 2 loops, we can have cell processing that work on single cell. And after the column loop finish, or the inner loop finish, we can have some processing over here. And for the whole nested loop finish, we can also have the outer loop processing, something like a calculation of the grand total. Here is one example of the 9x9 multiplication table. On the right hand side, we have the same algorithm I showed in the previous slides. On the left hand side, I had the implementation for that 9x9 multiplication table. So first, we set the row index I to be 1, and then each time we go into this row index loop for the while loop over here, and at the end we update the I by increasing it by 1. And then, before we go into the outer loop, we need to set the sum to be 0. Sum will be the grand total for the whole multiplication table. And then each row, for the same multiplicand, will sum up for the whole row. And row sum of 0 is not used, so we actually use row sum of the 1 to 9. So when we get into the row loop, we set the column index j to be 0, and set the sum for that row to be 0 as well. Then we go into the column loop or inner loop, and then each time we sum up the multiplication table contents to the row sum. And also print that multiplication cell out and with one space. And at the end of the row, we change a new line and also sum up the row sum to the total sum, the grand total sum. And at the end, we print that sum out. Right here, I will start some discussion about 2D array indexing for traversal. For a loop like this, we simply just print out cells. We have inner loop and outer loop, and we print out each of the cells for row and column. If we begin row from 0 to the m.length, and column from 0 to m to the row length minus 1, we starting from row 0 and finish all the column, and then row 1, 2, 3, 4. The second one is later. If we started from row 0 to row m.length minus 1, while column was starting from the last column back to 0. By doing this, we will end up with such an order from 4 to 0, from 4 to 0, something like this. That's the order of the execution for traversal. Similarly, if we set row like this, we will get started from the row 4 to row 0, and column 0 to column 1, so we get started like this. To traverse over the whole M table. And if we study like this for row and study like this for column, we study from here to here, like this, to traverse over the whole M table. And that is the row measured index For column measure, if we set the outer loop by column, and we start it from 0 to m, 0 the length, and row from 0 to the number of rows, we'll get started from here to here, that is vertically running. And if we start it from the last column back to the 0 column, we'll be going like this. And if we start the column like this, and then row like this, we will be going like this order. So you can study the algorithm's index and find out how it executes. And then we started from column like this, by column measured, and then row like this. We'll get started from here to here, like this, to traverse over the whole M table. And if we do not traverse over the whole M table, we just traverse over part of it. Say row we started from 0 to 4, but the column we started from 0 to less than I plus 1. So it will be end at j equals I. So when j equals I happen, we actually start at I minus j equals 0. So from this chart, we started from column 0 and end at the column that has I minus j equals 0. So 0 minus 0 is 0. 1 minus 1 equals 0. We start over here. So we go like this. This is how this indexing will work for traversal. On the other hand, if we get started from row 0 to row 4, but each time we get started from the end of the cell and then go back like this, we will get started from the m length minus 1 minus I. So the math will be like this. I plus j equals m dot length minus 1. So I plus j will be equal to 4. So these cells are the I minus j equals 4. So by calculating this, 4 minus I will be the initial value for j, so it will be on this line. So you get started from here to here. You had a partial array traversal. And also if we change the step size by 2, we will be hopping like this. We skip each other one. And if we want to do copy, say we want to copy this 2x2 submetric to another 2x2 submetric over here, and we started from I equals 0 to less than 2, so we'll be 0 and 1, but the row and column will be this 2x2 matrix. But we move 0, 0 point, move to 3, 3 point, we would be able to do copy by this mapping. So I and j will become the relative location of these 4 cells. And 0, 0 transition to 3, 3 would become a transition vector of 3, 3 from 0, 0 move to 3, 3. So each cell, the relative address plus the transition vector will have the destination location. For each ij you have here, the destination will be 3 plus I and 3 plus j over here. And after the copy, if we clean up the original location, it will become move. So the red dot will be moved from here to here. It is similar to the copy. For flipping, if we want to flip from column 0 to column 4, from A to B, and then we will need to have the symmetric line. This symmetric line's index will be half of the sum of the A plus B. And then we will know that A plus B will be 4. And then B will be 4 minus A. And 4 is M dot length minus 1 minus A will become B. So we know the index for B will be like this. So we started from the row 0. And for each row, we calculate the original j will be this 0, starting from 0. We copy over the column here, now m dot length minus 1. up to the center line, that would be m dot divided by 2. So this will finish the flip function. Each green column will be copied over here, blue as well, red will not be changed. For area shift, if we want to shift off the column 0 to 1, 1 to 2, 2 to 3, 3 to 4, then what we should do is we run through all of the rows, and for each row we started to copy the last element of that row to a temp value, and then we move this value next to the last one to 4, so 3 to 4, and then 2 to 3, 1 to 2, and then 0 to 1. So we started from j equals m0.length minus 2. That will be this 3 if the length is 5. And then stop at the j equals 0. And each one we move like this. 3 to 4, 2 to 3, 1 to 2, and 0 to 1. And after that, we put the temp value back to the 0 location. And then we run through all of the row I. By doing this, we will be able to copy the fourth column to temp, and then move from 3 to 4, 2 to 3, 1 to 2, and 0 to 1. This lecture shows you how the indexes are handled for 2D arrays. Thank you.